Okay, good morning. Today we're going to continue the growth of functions. So, functions. And we're going to start with the following definition. Right, so definition. Okay, so let f and g be functions from the set of positive integers, the reals. Okay, so we say f is big omega of g. Maybe I should write it like this. F is big omega of g if there exists constants c and k so that the absolute value of f of x is greater than or equal to c times the absolute value of g of x whenever x is greater than k. Or greater than or equal to it, it doesn't matter. Okay. So with big O notation that we introduced last time, we were bounding f from above by some constant multiple of another function. With big omega notation, so this reads big omega f of g. So with big omega notation, we're bounding f from below now. So this is just a different way of bounding our function f. Okay. So looks like it may be an example. Just pick some random example from textbook. So 3x squared plus 8x log of x is big omega of x squared. That's what it should be, I think. Yeah. Okay, so we just have to show that there are witnesses c and k so that that is bounded from below by some constant multiple of x squared. So to show that, let's just take the absolute value. Okay. Now, if x is greater than 1, this is going to be positive. This is equal to 3x squared plus 8x log of x, when x is greater than 1. It's greater than or equal to 1, doesn't matter. All right. But now, okay, log x, right? Log x is, well, let's see. So we want to somehow bound this from below. right? Now, this is going to be positive right here. 8x times log x is positive, right? So, again, this is positive whenever x is greater than or equal to 1. So if we drop that term there, this is surely the case, right? Again, we're assuming that x is greater than or equal to 1. And then we're done because this is equal to 3 times the absolute value of x squared. And all of these inequalities and equal signs again follow when x is greater than 1. So we just have to take c to be 3 and k to be 1. And then we found our witnesses, and this function is bounded from below by a constant multiple of that function. Okay?
Professor?
Yes.
I saw this question in the textbook. Couldn't we take the 8x log x, and then push the x to the log x and make it 8 log x squared?
That would not, so if you brought this up as an exponent, it would be x to the power x.
Yes. Oh, no, that's okay.
But yeah, like noticing those little things does help. So for example, okay, so this shows that that function is big omega of x squared. Just because this is a positive term, we just drop it away, and that's clearly greater than or equal to that. That's equal to that. So done. That function is big omega of x squared. But also, okay, so this is true. But also we can note that 3x squared plus 8x log x is also big O of x squared. This doesn't always happen, but I'm pretty sure that it's going to happen here. So we've shown that, so this is good. We haven't shown that. Let's see if we can look at that. Let's see if we can bound it above by some constant multiple of x squared. So an absolute value, look at this guy here. Now then, if x is greater than or equal to 1, we can drop the absolute value. So now, if we're trying to show big O, we want to get an upper bound now, not a lower bound. Okay? So what I'll notice is that this is less than or equal to 3x squared plus 8x times x. Now, why is that? Well, this piece right here is less than or equal to this piece right here. Right? So log x is at most x. Okay? So because that's greater than or equal to that, I can replace that with x. Right? So I can just write this inequality here. But then I have 3x squared plus 8x squared. Right? These two x's are multiplying. So this is going to be what? 11 x squared, which is equal to 11 times the absolute value of x squared. Again, x needs to be greater than or equal to 1 in order for these to string together. But okay, so that means that we take c is equal to 11, k is equal to 1. We found our witnesses. So indeed, it's the case that this function is omega x squared and also big O x squared. So those are finding the witnesses. So that would prove that part there, which leads me to my next definition. So if f is big O g of x, and f of x is big omega g of x, then f of x is order g of x. They have the same order. Okay? So the notation that we use for this is a big theta notation. We say f of x is big theta g of x. So this is big theta notation. Okay. So again, when you say that f is order g of x, that means the same thing as f is big theta g of x. So here, since we proved these two statements here, this means that 3x squared plus 8x log x is big theta x squared. They have the same order, which you should interpret that as f, this function here, call it f, and this function here, call it g. F and g more or less grow at the same rates as x grows to infinity. That's how you should interpret it. Because, so if you think about it, a function being big O of another one means that it's bounded from above by that function, by some constant multiple of it. And then if it's also big omega, then it's bounded from below by that some constant multiple of that function. So in a sense, it's kind of like squeezed in between the two as x grows to infinity. So they basically, they behave similar, or by not some constant multiple of difference. Okay. So let's look at some other examples of big theta and big omega and big O. Okay, so I'm just going to pick random examples from the textbook, or from the Rosen textbook. Let's see. So this type of question that I'm going to write down would definitely be something that would be on the next exam. So let's say, show 3x squared plus x plus 1 is order of big theta 3x squared. Okay. So this is definitely a type of question that would be on the exam. So let's look at a solution. So to do this, we need to show that it's big O of this function and also show that it's big omega of that function. So, all right, so maybe something like, so maybe first we show 3 of x squared, 3 times x squared plus x plus 1 is big O, 3x squared. Okay. So to do that, look at the absolute value. Now again, if x is greater than or equal to 0, we can drop the absolute values here because then this will be positive. This is when x is greater than or equal to 0. But then, if we're looking to get an upper bound, we're trying to show big O notation here. We can say, okay, if x is greater than or equal to 1, then x squared is going to be greater than or equal to x, right? So this will be less than or equal to 3x squared plus x squared plus x squared for x greater than or equal to 1. So that term is larger than that one, that term is larger than that one. Okay. So this is equal to, so 3, 4, 5, like that. I don't know why they put a 3 there, but I can go ahead and say that this is less than or equal to 6 x squared, which is equal to 2 times, and again, this is whenever x is greater than or equal to 1 at each step. So to see 3x squared plus x plus 1 is big O of 3x squared. Take c is equal to 2 and k is equal to 1. Okay? So that'd be like part 1 of this problem. So then next you would say, so next we show 3x squared plus x plus 1 is big omega of 3x squared. To be show it to be big O of 3x squared and big omega of 3x squared, then it's going to have order 3x squared. It'll be big theta x squared. All right, so I'm not going to have enough space here, so suppose this line was written right there. Now we have to show, so that we can bound this function from below times x. And that actually is going to be really easy in this case because we just can drop off those positive terms. So this is equal to 3 squared plus x plus 1 whenever x is greater than or equal to 0. And then if x is positive and that's a positive number, then this is surely greater than or equal to 3x squared, which is equal to, let's say, 1 times that, right? And again, this is provided x is positive. So let me say, see this function is big omega of 3x squared. Take witnesses, c is equal to 1, and k is equal to 0. And then finally, you would say, since 3x squared plus x plus 1 is big O of 3x squared and big omega of 3x squared, we have shown 3x squared plus x plus 1 is big theta of 3x squared. And then that's it. Okay, so I guarantee there will be a question like this on the first exam. See if I can pick some other ones that look similar, just to give you some more examples. Oh, sometimes I won't give you a function to find an estimate on. I'll say find a function, and that provides a big O estimate on a given function. So let's look at one of those. So maybe something like give as good so give as good a big O estimate as possible for the function f of x equals to x squared plus 8 times x plus 1. So not only give a big O estimate for this function, but also give the one with the tightest values for c and k that you can. And so these solutions all look more or less the same. You just start with absolute value, and for big O, you look for upper bounds. For big omega, you look for lower bounds. So here, we're doing big O, so we're going to look for an upper bound. So the absolute value of f of x here is the absolute value of this product. Now, we just have to ensure that everything in here is positive, so we can just take x greater than or equal to 0. So you can drop the absolute value sign. So This will work whenever x is greater than or equal to 0. That product is going to be positive. So next, might as well work out what this is. So we get x cubed plus 9x squared plus 8. Oh, no, wait a minute. What am I doing?
How'd you get 9x squared?
What was that?
Never mind. You got it.
And then 8x plus 8. And again, we're still assuming that x is greater than or equal to 0. Okay, so it looks like, so this is a polynomial of degree 3. So I know that based off of that theorem that I gave you last time, that this is going to be big O of x to the power cubed. I just don't know what the constants are. So I do know that if x is greater than or equal to 1, then x cubed is greater than x squared, and x cubed is greater than x. And then also, I'm just going to make sure that x is greater than or equal to 2, so then x cubed would be greater than or equal to that 8. So if x is greater than or equal to 2, then we know that this is going to be less than or equal to. So this one stays the same. Now that is less than or equal to x cubed. That's less than or equal to x cubed. And that is less than or equal to x cubed. Again, because x is greater than or equal to 2, 2 cubed is 8, so still it holds. So 8, 9, 10, 11. And again, we're assuming x is greater than or equal to 2. And then this will be equal to so now we'll just finish this by saying taking taking works. Taking c is equal to 11 and k is equal to 2. We have shown f of x is big O of x cubed.
How did you get the 2? Like, why did you choose 2?
Because I wanted, so like, I wanted x cubed to be greater than or equal to that. I wanted x cubed to be greater than or equal to that, which would happen if x was greater than 1, greater than or equal to 1. But then I also wanted x cubed to be greater than or equal to 8.
Okay, I see.
So if I pick 2, then 2 cubed is 8, so I can justify it by just getting rid of that 8 there.
Okay, I see.
Right, so, and then this would be the solution to that. I mean, that's it. Okay. So, let's look at well, I'll leave one up for you to kind of work on your own. So same type of question, but then maybe something like x log x plus x squared times x cubed plus 2. Yeah. So this would be a good problem to work on and try to find the solution. And then on the exam, I'll give something similar to that exact problem. Which again, the exam is going to be posted at the end of next week. We still need to cover some material this week and then have a review at the beginning of next week. And then I'll post the exam at the end of next week.
So, Professor,
Yes.
if we do the same solution for the big omega, so can we drop like x squared plus 8x plus 8 for the big omega?
Yes.
For the big omega solution.
Say that one more time. So what about that problem, the 8x or the x squared plus x?
Like the solution you did, like you just erase, so we can drop the 8x squared plus 8 for the big omega.
Yeah, so for the big omega, you would just drop that immediately. Because they're going to be positive numbers if x is greater than or equal to 0, then if you're trying to get a lower bound, you just don't include those positive numbers that you're adding, and then you would get it. You would get that this function is also big omega of x. Not this one, but the one that was up there. Was also big omega of x cubed.
Okay, thank you.
Mm-hmm. Okay. So problems like this you should pay attention to, and then
Will you work this problem with us, please?
yeah.
Okay, thank you.
So again, to do this, you always start by just considering the absolute value of the function, right? And you want to ensure that this is positive in here, and one way to do that, in this case, is just make sure that x is greater than or equal to 1, and you can drop the absolute value function. So x log x plus x squared times x cubed plus 2. And now you can just do a little bit of algebra here and get that this is x to the power 4 times log x plus 2x log x plus x to the power 5 plus 2x squared. And again, we're assuming that x is greater than or equal to 1. Okay, so I see that here the highest exponent for my x is 5. And then I have these logs here, but I know that log x is always at most x. So what I can do is I can replace each of these log x's by x and get an upper bound. So replace that log x by x. Replace that log x by x. Leave everything else the same. So then, what does this become? So this is at most that. And this is going to be equal to x to the power 5 plus 2x squared plus x to the power 5 plus 2x squared. So combining, we have 2x to the power 5 plus 4 times x to the power 2. And again, we're still assuming that x is greater than 1 for all of these to hold. But now, if x is greater than or equal to 1, then x squared is at most x to the power 5. So this is at most 2x to the power 5 plus 4 times x to the power 5. So, and then this is be equal to 6 x to the power 5, which is equal to 6 times the absolute value of x to the power 5. And again, this is whenever x is greater than or equal to 1, that we can establish these things here. So then you would say, taking witnesses C equal to 6 and K equal to 1, we've shown that f of x, this function here, is big O of x to the power 5. And this one wasn't so bad once you worked out the algebra, and then you remember that right there, that log x is always at most x, and then you can string together these inequalities and get the upper bound that you want. So if you're looking for practice problems, I would say, let me just pick some. Section 3.2 of the Rosen book, I would say problem 10, 11, 14, 20, 21, 25. So I'll write these on the board in a second, just kind of 27. And 34. So this is all from the Rosen textbook. So section 3.2. 10, 11, 14, 20, 21, 25, 27, and then 34. Those would be good problems to look at for possible questions on the second exam. Okay. And then section 3.2, 3.1, excuse me. I'd say 5 through 21 all. And we haven't gotten to section 3.3 yet, but we will. Next time. I'd say 3 through 9 all. Yeah, it should be fine. And then there will be a few questions on sets and functions. So section 2, 3, maybe something like $14, $15, $22, $23, $24, $25. And then section 2, 2, three, 4, $20, $21, $22. And then 53 through 57. All right, so that should cover like maybe one question from there, one question from there, one from each of these sections with like multiple parts to it, like parts A and B or A, B, and C. Okay. All right, so that'll be it for today. Next time we will pick up on complexity of algorithms. And then after that, we're going to have a review day, or maybe one more day on complexity of algorithms after that, then a review day, and then you'll get the exam. Okay, so that'll be it. Everyone stay safe, and I will see you on Wednesday.
Thank you.